Good morning. What better time to learn about Apache Spark than the morning after the reInvent party? Let me make you feel at home. Doop, 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 doop. Well, thank you for coming to our session. Very humbled that you took the time after the party to come to our session. My name is Abhishek. I run product management for Amazon EMR and Amazon Athena. This is Mert, who is a big data architect in our team, and also the beauty and the brains behind our operation. So what we're going to do today is, in the 60 minutes, we'll show you a couple of demos, and we'll also talk about some of the major improvements that we have made on our product in the last 1 year. All of them will help you run Spark better on top of the EMR platform. It will sound like a quick-fire session where we will talk to you about a lot of new things that we have done in the last 1 year. So let's get started. All right, so what we do see is data engineering platforms are evolving, and there's a common pattern across multiple data engineering platforms that you have clients like notebooks or edge servers that are on one side, which are used by data scientists and data engineers. Then you have orchestration systems, and the most common ones that we see are Apache Airflow and AWS Step Functions. And then at the very bottom, you have EMR clusters. Most customers, when they move to EMR from running on-prem, choose either a long-running cluster or a transient cluster. They choose a combination of any one of these methods to run on the cloud. But the thing that is really common is both of these clusters are processing data from the same S3-based data store. So why do customers choose these patterns? In an on-prem world, a Hadoop cluster is a shared multi-tenanted environment, or a Spark cluster is a shared multi-tenanted environment. When customers move onto the cloud, they are able to decouple storage and compute. And when they decouple storage and compute, new architecture patterns come into the picture. Because what you can do is you can keep all your data in S3, and you can either run a transient cluster like a pipeline, or you can run a persistent auto-scaling cluster continuously. So when do you run which? How do you decide? So long-running clusters, which are auto-scaling, are really good for lines of businesses, really good for short-running jobs. So what we have seen is in organizations, there will be different lines of businesses, and each line of business is given one persistent long-running auto-scaling cluster, where you can individually, where multiple people can just run jobs on the cluster. If these jobs are shared, if these jobs are short-running jobs, then the cluster can auto-scale for these jobs, so on and so forth. It's ideal when you're trying to save cost on the multi-tenanted environments. Transient and job scope clusters are really good when you try and run them from long-running jobs. Anything on the periphery of a 30-minute or more feels like a long-running job. What it allows you to do, it allows you to separate those jobs into individually run job scope clusters. And the biggest benefit for that is that you can separate production pipelines from non-production pipelines. You can separate multiple production pipelines. And if one of the pipelines fails, then the other pipelines don't have to suffer. Also, you can upgrade each of these pipelines or each of these clusters independently. So operationally, it's just much more nicer and easier and cleaner to run a lot more transient clusters for long-running pipelines. So when we think about our product, we think about making improvements in all of these sections. We think about clients, such as we have EMR notebooks, which is our fully hosted Jupyter-based notebook. We have orchestration layers, so customers use Airflow. We also integrate with AWS Step Functions. And then we call the most bottom layer the execution layer. So what we'll talk about is improvements that we have made in any of these segments, in all of these segments. So the first one is we introduced a new runtime environment for Apache Spark in 5.26, which was released about 3 months ago. And in EMR 5.28, which was our latest release in November, we have switched on this runtime environment by default. So what is this runtime environment? This runtime environment is a performance-optimized version of Apache Spark that is 100% compliant with the open source version of Apache Spark. That means we are not breaking any API compatibility. We are not changing how you use Spark. If you're using Spark 2.4, it'll run perfectly fine. But we are adding performance optimizations that make Spark run faster on top of EMR. So when we compare ourselves to the version we had last year, which was without the runtime and which was plain vanilla open source Spark, we are roughly about 2.6 times faster than with the runtime environment. So if you compare Spark 2.4 running, vanilla Spark 2.4 running EMR 2.6 last year to this year, I think there is a significant performance improvement. These results that you see are all based upon TPC-DS tests. We took about 3 terabyte data sets and ran those tests, and that is our benchmark. Take these benchmarks with a grain of salt. What really matters is when you run your workload, your performance may vary, but we have a high amount of confidence that when you move from an older version of EMR to a newer version of EMR with performance optimized version, I think you will get a shorter runtime and you will save a lot of costs. Here are a couple of other scenarios. So if I look at the total runtime of TPC-DS queries, it has reduced by 2.5x from the previous version, or the previous open source version without the runtime. And then when I look at a geo mean, it has also improved significantly. So let's dig into what's happening. So if I take a cross-section of long-running queries, and by long-running queries, I mean queries that run anywhere north of 90 seconds or more, we see roughly about 5x improvement in long-running queries. So this graph shows you the TPC-DS queries, and on the y-axis is the average speed up when I compare it to the open source version without the runtime. We also see about 2x improvement in short-running queries. So these are queries that are still running on 3 terabytes of data, but run for about less than 90 seconds. And we see about roughly 2 times improvement in the short-running queries. All of these improvements are coming from either configuration changes, query planning optimizations, better way of running the execution engine on top of EMR. So for example, what we learned with short-running queries is the Spark dynamic executor waits till it can really compute how many executors it needs to run. And once it has understood how many executors it needs to run, it starts spinning up those executors. So if you're running a query or if you're running a job that is really small, it kind of adds a little bit of variance, a little bit of latency towards that. So we added a new technique that eagerly allocates executors before even the job starts, and that immediately you can see that improves performance. So on this graph, you will see that what was the job runtime on the x-axis. So you will see that it majorly impacts jobs that were on a short runtime frame. And you can see on the y-axis, you will see the average speedup that we get across queries. Now, you don't have to do anything to get these performance improvements. You just have to upgrade to the new cluster, to the new version of EMR. All of these changes are switched on by default, and you'll be able to run these without a problem. There are other improvements as well. For example, we added improvements around dynamic partition pruning. So most of you who come from the database world probably understand what dynamic partition pruning are. Basically, we are reducing the amount of data that we are reading based upon intelligent pruning of partitions on really large tables. And you can see that it adds a significant amount of performance improvement to long and short-running queries. Again, 100% compatible with open source APIs. We are not breaking any open source APIs. Your workload we run exactly. These are just query optimization techniques. There are other things that we have done, like for example, we added some work on data prefetch that allows us to prefetch the data so that we can better utilize the CPU. So if you look at all the performance optimizations, it kind of falls into any of these categories. There are configuration, driver executor conf ratios, there's heap memory ratios, overheads, instance details. There are things like dynamic partition pruning, which fall under the bracket of planning and optimization. There's data prefetch, which falls under query execution. And then there are improvements in the job startup time, like eager executor allocation. So with all of these, what we're saying is the newer version of EMR runs Spark much faster than the previous version. And if you do migrate, it is an automatic discount that you get because EMR charges you by the second. We have seen customers that have the previous version running for 4 to 8 to 16 hours, and when they have moved to the new version, the job run times have significantly decreased. And when the job run times decrease, your cost automatically goes down. So that is the first one. The second one is we have added a new component to EMR. We've taken Apache Hoodie from open source, and we are working with the team at Uber who came out of Apache Hoodie. So what Apache Hudi allows you to do, it allows you to add record-level insert, update, and delete semantics. So let me talk a little bit about why this is important. So as you all know, building data lakes is very simple. We do it all day. I'm joking. It's not really simple. There's a common pattern on building data lakes, and especially data lakes on S3. Most of the data that is coming on from in your data lake are coming from either applications or databases, change data capture from databases, or external sources or streaming events. The most optimum way of doing this, if you were doing this in a data warehouse, was you put it in some intermediate storage, you ETL the data, you create tables and derive tables, and you let your analyst query those tables. Fairly simple logic of how data warehousing also works. When you build data lakes on S3, and because S3 does not have native insert, update, and delete semantics, people start to have workarounds. So what are those workarounds? That most S3-based data lakes tend to have a raw data storage location, or raw tables, where you take the raw data that comes in on an everyday basis. And because you can't update your tables that you had from yesterday, you run a new ETL pipeline that recomputes the entire data set. So for example, imagine I'm an e-commerce company, and I have items in my catalog, and every day I'm creating a table of what was the sales in the catalog. So from yesterday's data, I have some new data that comes in today, which says that item 1 and item 3 and item 5 had new sales. Now, that raw data arrives in S3, and I want to create a computed new table that allows me to see sales for all the items. All the items haven't changed. What do you do on S3? You take the old data sets, and you recompute the entire pipeline again to create a new table. Right? That's because S3 doesn't give you update semantics. In a data warehouse or in a database, this would be slightly simpler. What you would do, you will go to the table, and you will apply the incremental change records onto top of the table. So because of this native ability for S3 not to have update and insert semantics, we see write amplification. That means you are adding a lot more write, and you're rewriting a lot more data many times. And that starts to become a problem when you have a lot more data that is coming in, and you're recomputing all the data again and again. So there are other use cases that are also pretty difficult, if my slide will decide to move. All right. For example, data deletions or row-level deletes of data to adhere to privacy principles tend to be very difficult. It feels like for data deletion today, to delete a line in a book, you're republishing the entire book, right? Because you can't really just go and delete a record of the data that is sitting in S3. So it becomes really hard, and it becomes really expensive to deal with regulations such as GDPR and CCPA, because S3 doesn't give you delete-level semantics. S3 gives you a lot of other benefits, and that's why more people build data lakes on top of S3 than anywhere else. Right? But these are the shortcomings that we see, and that's what we're trying to address with Apache Hudi. Also, change data capture. Change data capture is probably the most common source of data that comes into a data lake, because it comes from a database. And you're not taking the entire raw dump of a database every day. Or today, maybe you are. But it's not the most optimal way of doing things, where you take the raw dump of the database every day and recompute the entire table on an everyday basis. The best way to do it, or the way that databases generally do it, is you take incremental data, you take change data capture, and you apply it to the data on the data lake. That's what Hudi also allows you to do. Streaming ingestion and time-ordered data also becomes a problem, because you might have duplicate records, your schema might change, so on and so forth. Hudi came out of Uber. It was developed in Uber, and the folks at Uber were very nice to kind of donate it to open source. So it's now an Apache open source project. It's an incubating project. We've been working with the Uber team for the last 6 months. We've made a lot of contributions to the team, and we'll continue to do so. So what was Uber's motivating use case? It was very similar. There was a trip store which used to account for all the trip-related data. And when you get an incremental update in the trip store, you would see that incremental data not only impacted today's tables, it also impacts last week's tables, yesterday's tables, last month's tables, and last year's table. These are all derived tables. So there is, again, you see a huge amount of write amplification. The problem became a lot bigger when you have more and more tables, so you start to run a lot more ETL pipelines, a lot more Spark pipelines to recompute all of this data again and again. So in their case, they had an HBase table, and the HBase table was roughly about 120 terabytes, and they were recomputing those HBase tables on an everyday basis, and it would take 8 hours for just incremental 500 gigs of data. So spinning pipelines for 8 to 9 hours to recompute all of the data to accommodate 500 GB of incremental data sounds like something that we need to fix. So that's where Hoodie comes into the picture. So what is Hoodie? So Hoodie is an open source project. It's a storage abstraction. So it's not a new storage format. Your data in S3 doesn't change. It's not a replacement for S3. It is a storage format implemented as a library that runs on your Spark cluster. So it runs on your Spark cluster. It also, their libraries also need to be integrated in any systems that you're using to read the data. So if you're reading data via Hive or Presto, the libraries will need to be integrated with that. So the storage abstraction writes data in a way that allows us to simulate updates, inserts, and upserts into the data set. And it does that by writing snapshots of files and writing the files in some sort of a timeline. So why should you care about this? You can get near real-time ingestion. Your batch jobs become much, much, much faster because now you are not recomputing the entire data sets. You're just updating parts of the data set as and when incremental data arrives. You get one unified analytical storage. So your underlying data set doesn't change. It still is in Parquet. It still is in Avro. Parquet and Avro is what Hoodie uses. Your data in S3 doesn't change, but the format in which we write it, the abstraction in which we write it, is guided by Hoodie. Also, for those of you who are kind of building Lambda architectures, that you have a slow batch layer and a fast layer because streaming data has different requirements from batch data, Hoodie allows you to consolidate them into simple pipelines, and I'll show you how. You also can do row-level deletions because it simplifies data privacy. Also, so we think it is really great building blocks for great data lakes, and all of this is open source. All of this is in open format, so there's nothing proprietary about the system. So technically, what are the primitives that we are supporting? So we are supporting a fast, or Hoodie supports a fast upsert-based system that allows you to, with a pluggable indexing mechanism. It allows you to atomically push the updates with rollback and save points. That means you can go back in time. Really useful for real-time data if you have dirty data coming in or if you have to recompute data sets. It gives you snapshot isolation so that readers and writers see the same data. Because S3 is eventually consistent, you can have multiple pipelines writing the same data set, and therefore readers, if you don't use consistent view, readers might see different forms of the data set. In this case, snapshot isolation allows you to all the readers to read exactly the same data set, right? So if you're familiar with databases, these are concepts that are not new to databases. They've been implemented on databases for a really long time. What we're doing, what Hoodie is doing, is creating an abstraction built as a library that allows you to get those transactional semantics while keeping your data in S3. It also allows you to manage file sizes. We'll talk a little bit about that. There are async compaction mechanisms, so you can add more, you can compact your data sets. And then there is the timeline to track lineage. Because remember what Hoodie does, it writes snapshots or logs. There is a timeline of when the snapshot or the log has changed. And therefore, you can go back in time and revert the table back to an original time when the data was there. So to understand Hoodie, you have to understand because I said it is a storage abstraction. There are two kinds of storage abstraction that it exposes. One is a copy and write abstraction that is useful for read-heavy workloads. The second is a merge and read abstraction that is used for write-heavy workloads. So when you write your table, you select that what storage type do I want to write it as. You can use both of them together, so on and so forth. But depending upon what do you want to do with that table, you choose one versus the other. Each storage abstraction also exposes a bunch of views. So what do these views mean? What do these views do? So for example, the copy on write storage abstraction exports two views, a read-optimized view and an incremental view. When you query the read-optimized view, you get the entire table. But when you query the incremental view, you only get the incremental data sets that was updated on the table. That is really useful if you want to trigger pipelines on incremental data sets. So let's take an example. So in this example, in some table, I want to insert four data sets, A, B, C, D. So at commit time is equal to 0, Hudi will write these file blocks. So in this case, you'll see file block as A, B, file 1 as C and D, and file 2 as E. Now at time t is equal to 1, we will change the D. That means update the D to D dash and A to A dash, right? So what Hudi will do in this storage format is they will write a new file or a snapshot of the file with only A dash and another snapshot of the file with the change D dash. So if you query the read optimized view, you will get A dash, the updated data set, B, C, D dash, and E. And if you query the incremental view, it'll only give you the incremental data sets. So as and when more data comes in, the incremental views and the read optimized views kind of work exactly the same way. When do you use it? When you're writing the entire table and partitions and you're dealing with updates, which we think is the most often used use case. When you know your workload fairly well, that means these are ETL pipelines that you expect to run almost all the time. If you're already using Parquet on your table, this is great because it uses Parquet underneath the hood and it gives you exactly the same kind of performance. And it is operationally very simple. So if you create this copy and write storage format and you go into S3, you can see all the snapshots of the data that I just talked about. But your execution engines like Spark and Hive, they don't see it. They basically see the updated data sets. The other one is a merge and read storage view, which is slightly different. And it also exposes a new view called the real-time view. And because of this, you remember what I said about Lambda pipelines, that you can actually just merge those Lambda pipelines into a common pipeline? The real-time view actually allows you to do that. So what happens in this in merge and read? In merge and read, I won't, whenever data changes, we write a log. This is a log of what has changed in this data set. So notice the views. So the real-time view is getting the updated data sets in this particular view. The incremental view is again getting the updated data sets, but the read-optimized view is not getting in the data set. Because the merge and read is optimized for writing these logs really, really quickly. So at t time, at t is equal to 2, I may also add new data sets. As you can see, all the real-time view will give you the new information. The incremental view will also give you the information. But the read-optimized view will not give you the updated information unless you do a compaction. Now, this compaction can be done offline. This compaction can be done using a process that is offline. And when you compact these data sets, your final data sets become what was the update. All the views kind of merge together. So when do you use this view? So if you want your queried data to be available as soon as possible, this is optimized for writing as quickly as possible and giving you what was the real-time stream quickly. And also, if your workload has sudden spikes. So when what does Hudi give you? Hudi gives you an ability to comply with your data privacy laws. Hudi gives you ability to consume real-time streams, reinstate late arriving data, track change, and roll back. So there are a couple of sessions. They're already done, but you can go and watch these videos of these sessions as well on YouTube. And now we'll show you a quick demo of how Hudi works. Mark?
Thank you, Abhishek. Hello, everyone. Thank you for coming. In this demo, I'm going to show how to work with Hudi on EMR. So within this demo, we're going to do a few things. We're going to build a Hudi data set from some source data. We're going to update some rows from that data set. We're going to delete some rows. And then we're going to query it in various ways just to demonstrate that. Just a word of caution, there's some code here. If you enjoy it, awesome. If not, hopefully it'll make sense. So let's get into it. The first thing we're going to do here, I'm going to read some source data. The source data that we'll be reading here is one of my favorite data sets. It's a publicly available data set that Amazon publishes for product reviews for the items that they sell on their website. In this case, this data set has some interesting information like review ID, the customer who provided that ID, the product title for that, a star rating that customer has provided, and the date of when that review was done. So the next step, let's create our Hudi dataset. And while that's running, let's kind of dive into some of the options that we set within Hudi. So the first thing that we set is the table name. In this case, we're setting the table name to Amazon product reviews. The next thing that we're setting is the storage type. As Abhishek just mentioned, we chose copy and write here, but you could also set this to merge on read. The next options that we're setting is the record key, which is what I like to look at it as a primary key for a record. In this case, we're using the review ID for that. The next is a pre-combined field, which is if there's two rows of data with the same record ID, look at this column and pick the row that has a greater value. So in this case, I'm using a timestamp. And then the next one is the partition path. So which column should I be using in order to partition my data set? The next block of options is the tight integration with Hudi and a Hive metastore. So if you want to be able to query this data using Presto or Hive, or use the metastore for other things, Hudi can automatically sync the metadata that it generates into your Hive metastore. So we're enabling this. We're calling the table the same thing as we did with the data set. We're telling Hudi not to assume what the partition format is. We're telling it I want to partition 3 ways by year, month, and day. And then we're telling Hudi use this multi-part keys value extractor as a way to look at that column and split it up into those 3 columns. So to write the Hudi set, it's very similar to how you would write any other data set. The format we're setting here is org Apache Hudi. We're telling Hudi, we're giving an operation, that this operation that we're doing right now is a bulk insert. You could also set it to insert and upsert. But in this case, since we're creating it, we're choosing a bulk insert because it's a little bit quicker. Next, we're just going to override any data that already exists in my path and provide it the path that I want it to save it to. So again, reading the data, very similar to how you would any other data set within Spark. And we're setting the format, we're giving it a path, and then away we go. So while that's running, let's look into the Hive metastore that I'm using on this cluster is the Glue Hive metastore. So here we can see that it's created a table for me, and then we can just dive into it a little bit. You'll notice the input format and the input format is a Hudi Parquet input format. And then when you look at the schema, you'll see some special columns that Hudi has created on our behalf to help it locate certain records pretty quickly where it's being stored on S3. So that is done. So let's just run this very simple query on this data set. In this query, we're just doing a group by on the star rating and getting a count. And what we notice here, usually Amazon star ratings is 1 to 5, but we see some star ratings that are 100. That looks kind of odd, and we'll probably want to clean that out. So what we want to do is, first, we'll select the rows that we want to update. So here, we're just filtering all of the rows where the star rating is 100, and then we're just nulling it out. We want to keep the records. And then we want to do the actual write to the data set. We pass in our Hudi options, like we did before. We set the operation key to an upsert operation, set the mode to append, and then hit save. And then this will go and update the data on S3. So while that's running, let's kind of take a look at how Hudi is storing the data. So this is a location in S3. Let me make this a little bit bigger. And then we see that partitions have been created. So we have 2015. These are the months. And then we can go in from the day and into the data set. But the other interesting directory we see here is this Hudi directory that we see here. So in this directory, we can see there's two commit files. These are the way I like to look at it, like manifest files that tells Hudi what is the latest files that we should be reading for this commit. All right, so let's just make sure that we've updated data. So we're just rereading the data, running the exact same query that we ran before. And what we're expecting here is that the star rating of null for 5 rows. So the data is now nulled out. So next, suppose a customer comes to you. You're operating maybe in Europe, and for GDPR reasons, they ask you to delete the data, their personal data. So what we could also do is delete the data. So in this case, we're doing very similar things. We're setting the format. We're passing in the options. The operation key here, we're using an upsert. And then the interesting option here that we're setting is the payload class, which we're setting it to empty Hudi record payload, which just instructs Hudi to say, instead of updating values for this row, I want you to completely just remove it. While that is running, let's take a little bit more deeper into S3. I'll make this a little bit smaller. So this is one partition, which has several Parquet files. One thing to notice is at the end of the Parquet files, there's the commit ID at the very end of the file name. And in this directory, we can see that the initial bulk insert that we've done created 6 files. But from the upsert, we only had to modify 1 file. So we just copied that 1 file, we made the change, and then we stored only that one changed file. So it didn't require recomputing the entire partition. All right, delete is done. Let's just validate that it's gone. So in this query, we're just doing a count for the customer ID that we just deleted. What we're expecting here is that we'll find absolutely no rows. And there we go. The next thing we're going to demonstrate here is kind of a point-in-time query where we can tell Hudi, I want to query data from one point in time to another. So in this query, what I'm doing, I'm just doing a select distinct on the Hudi commit time, and then get a list of the commits. In this case, we see 2 commit times. We've done 3 operations, but the third one is not there because we've removed rows. So it's not going to pick that up, but that's OK. And then in this block of code, we're setting the view type as an incremental view type. We're setting the begin time, which is 0. And then we're setting the end time to the first commit. And then we're just running a very simple query on all of the star ratings that were 100. That was the one that we nulled out. And what we expect from this output is those rows to show up again. And as we can see, we have our 5 rows. So that's one way you can query in Spark, but you can also query in Hive and Presto. So I have, within Hue, I have a EMR cluster that is running Presto, so we're going to run these queries on top of Presto. So the first query is very simple, just select star, limit 10, and we get some data. And because we are using copy on write, this is always going to pick up the latest version of the data. So if we run this query, which is going to filter for all of the rows with the star rating as null, and the customer ID that we deleted, what we would expect is only 5 rows of data, which is where the star rating is null. And there we go, we get 5 results. So I hope you enjoyed that. Back to you, Abhishek.
Thank you, Mert.
Thank you.
The demo gods have been nice to us today. All right, so let's talk about some of the other improvements that we have made. This time we'll talk a little bit about the infrastructure, the infrastructure optimizations. The first one we'll go talk about is Spot. I love Spot. Spot is excess capacity on AWS that you can get on top of EMR for up to about 60 to 70% discount. The drawback of that is that the capacity can actually be taken away. So if you have jobs that can actually withstand interruption, Spot is a really good idea. So how do people want to use Spot? What do we tell people as to how to use Spot? Yeah. So imagine this scenario where I have a 10-node cluster, and imagine that each of these nodes costs me $1. And let's say for this purpose, the job runs for 14 hours. So this cluster costs me roughly about $140. Now, assume that I added 10 more nodes on Spot. So my cluster has become a 20-node cluster, and in my fairy tale world, the 14-hour job has now reduced to a 7-hour job. Let's assume linear scalability for the example. So I have a 20-node cluster now running for 20 hours. Remember, the first 10 nodes are on-demand nodes. Those are at $1, and the other nodes are Spot nodes. And we would say that the Spot node is, let's say, something around 50% discount. So they're at 50 cents. So if you look at the total cost of this cluster, the total cost of this cluster reduces to, to about $105. So what you have done by adding Spot and scaling up your job because of Spot is 50% less runtime and 25% less cost. So what I tell my customers is, if you can take your cluster and you can divide the cluster into on-demand and Spot, and take the number of on-demand instances, that is the worst expectation from your business. So if your worst SLA to the business is 14 hours, and you need 10 nodes to always succeed in 14 hours, run those on demand. And then scale up maybe twice or thrice on an everyday basis using Spot. Every day when you scale up on Spot, your cost will be lower and the job will run much, much, much faster. And the day when you don't scale up on Spot or there is no Spot capacity left, you've also gone back to your basic costs and you've also met the SLA of the business. So people now, the cost of this cluster can be further reduced. For example, the on-demand nodes, I can then go and add them to a savings plan, and that will give me an additional 60% discount. So you get about 60 to 70% discount on Spot, and roughly about 60% discount if you include them on savings plan, the on-demand instances. So the cost of running the cluster can become really, really low, and also meet your SLAs. And every day when you get Spot, you will run faster and you will run cheaper. So you'll ask, what about interruption? How much do you get interrupted? Do customers get interrupted? So let me show you some data. So this is the data of how many clusters across the world get interrupted because of Spot interruption. So you would see, the number is pretty low, it's about 0.2%, but that was not good enough for us. So if you look at where the arrow is pointing, that was sometime last year in 2018 that we started reorganizing our algorithm, and we refactored our algorithm to take account of not only where the capacity was, but how fast that capacity was getting consumed. And because of that, you can see that the interruption rate since last year has been consistently very, very, very low for the entire period of the year. So if you're not using Spot instances today, you are actually leaving a discount on the table. Don't leave that discount on the table. So Spot is another thing that we've introduced in the last 1 year that we feel that will really reduce the way your EMR clusters run. Spark works wonderfully fine with Spot instances, no problems there. The next thing that we're doing is we're adding a new capability to EMR called the managed resize. A lot of our customers use auto-scaling clusters. Auto-scaling clusters are essentially you decide what metric you want to scale on. We will give you a simple API to define that metric. You decide when do you want to alert on that metric. And if the metric goes above a certain threshold, you can scale up or you can scale down. So we already have auto-scaling. We've had that on the platform for a really long time. What we're introducing now, and it's in beta, is a managed resize version. So the difference with auto-scaling and managed resize, in managed resize, you do not need to define any policies. You go to a cluster, you check managed resize, and you define what is the maximum and minimum you want on the cluster. That's it. We manage all the configuration. We manage all the metrics. We decide when to scale up. We decide when to scale down, so on and so forth. We also decide what metrics are required and when. So this is really for customers that found it hard or that they don't want to spend time investing and investigating their workloads and trying to use auto-scaling. If you are that, an auto-scaling functionality is also available. So let me show you a couple of experiments. So in this experiment, the blue lines are basically load patterns, right? So we took a cluster. This cluster was a one-node cluster. And we enabled managed resize on it and allowed it to scale to a 20-node cluster. And then we said, why don't we put some load patterns on it? And let's try putting some ad hoc load patterns on it. So we will put a lot of load, and then we give it a 30-minute break, then put a lot of load, then give it a 30-minute break. If you look at most ad hoc patterns, that's what you want auto-scaling to arrest. You want auto-scaling to be responsive to ad hoc workloads so that it scales up and scales down without any work. So the blue line shows you the amount of work that is given on the cluster. The line adjacent to the blue line, the one that is going along with it, is when we request scale. So you can see that we actually almost immediately request, the minute your workload starts to go up, we almost immediately request scale up. And within the orange line is when we have actually scaled up and scaled down. So from the time that we requested the scale up to the time we actually got all the nodes running and started consuming those capacity was roughly about 5 minutes. You can see it on the bottom scale. You can also see that as the workloads go down, we also gradually scale up. So the second part of this graph, the one in the middle, is the peculiar one, because what we tried to do was give it a lot of short-running jobs and see how it behaves. You can see that it behaved very well in scaling up and then delayed a little bit in its scaling down because it was trying to make sure that no jobs are actually canceled during the process of scaling down. When we compared this to running a fixed 20-node cluster, we found that an auto-scaling cluster would roughly save you, or a managed resize cluster would roughly save you roughly about 63% costs. Now, you can do the same thing with auto-scaling as well. It's just that managed resize, you don't have to manage the policies. We manage the policy. We do all of those things together. So on the infrastructure side, we have done a lot more work on scaling, which I just talked to you about. We have done work on Spot that will reduce your cost. We've also done some work on fine-grained access control of our multi-tenanted cluster. So early this year, we released AWS Lake Formation. AWS Lake Formation simplifies how you build your data lakes and how you enforce security across your data lakes. So with Lake Formation, you can define access control and permissions in one place, and services such as EMR, Athena, and Redshift kind of allow you to enforce the permission across query engines. So define in one place, enforce everywhere else. So Lake Formation is pretty simple. You go to Lake Formation. Your data is sitting in S3. Lake Formation is based upon the Glue data catalog. So the abstraction for Lake Formation is tables and columns. Based upon users or roles, you can set table-level or column-level policies. And irrespective of which engine you come from, whether you're using Athena or whether you're using Spark on EMR, we will enforce these schemas. Or we will enforce these entitlements. The reason we built Lake Formation was customers wanted one central face to enforce these entitlements. And most customers have a wide variety of query engines. They use EMR, and they use Presto, and they have Redshift in their environment. So it really simplifies the whole idea of adding entitlements to it. You can control data access by granting and revoking permissions to tables, because Lake Formation exports an interface around tables and columns and not objects and files as S3 does. All right, so let me show you a quick recorded demo. The chances of this demo failing are 0. It's recorded. So what we did for EMR with Lake Formation was, right now it works for Spark running on an EMR cluster. We also added an SAML integration component because we need to know who the user is. So if you're using EMR notebooks or using Zeppelin, we also integrate with a SAML provider. So what you will see in a demo is that we will open a Zeppelin interface. The Zeppelin interface is running on an EMR cluster, and as soon as we log into the Zeppelin interface, we will be sent back to the IDP. In this case, the IDP is auth0. We will log in using the IDP username and password. Then we will open the Zeppelin interface. We will query a table. We will get all the columns on the table. Then we will go to lake formation, and for that particular user, we will restrict one column, and then we will come back into the Zeppelin interface and see if we can query that column again or not. Right? OK, so here we go. Fingers crossed on a recorded demo. All right, so here I'm, well, clicking didn't work. All right, looks like my clicker is not working. Well, chances of a recorded demo not working is also good. So in this case, so let's go back and try that again. I think I may have just clicked through it. All right, you just trust me on it. All right, so what we ended up doing in this demo is in this phase, when you hit the Zeppelin interface, it goes into an auth0 interface, and we put in username and password. For example, in this case, it was Bob, and you can see on the right-hand side that Bob is now an authorized user. Now we'll go into the lake formation use case. And in this case, we will go and try and query a table arrow decimal. Oh, that works now. Well, so we will grant access to this particular table. And what we will do is just change a couple of things on this table. So in this particular table, we will just select, we will include a couple of columns. We'll include X and we will include Z. We won't include Y. So, and we'll give them select permissions. So when we go into the Zeppelin interface and try and query this table, you would see that we are only getting to query X and Z. All right, it looks like it doesn't like it. Well, doesn't like it. Doesn't like my GIF. Anyway, sorry, that didn't work. Well, so if that would have worked, and we would have gone into the yarn screen, and we would have looked at who the real users are, you could see that these real users are the ones that are coming from an IDP or from SAML. And we are basically doing user impersonation so that the exact user is being used into the cluster. So what really happens is when this user goes into and queries a table, the EMR cluster goes to lake formation, and based upon the identification of the user, requests credentials from the table for that particular table. So EMR is asking lake formation, well, Abhishek is trying to query table 1. Can I get short-term credentials for table 1? When the credentials are given by lake formation, then EMR cluster goes and queries the data in S3. So what that means is that you can take off all your S3-based roles that you have on an EMR cluster attached to an instance profile or attached to a cluster profile. You can take that off because you don't need any S3-based permissions to be accessed to users because lake formation is delegating the S3-based access control. A little bit deeper dive, so as to what's happening inside. So we have added 2 new agents or 2 new privileged processes on an EMR cluster, which run as different processes or as privileged processes. One is a secret agent, which securely communicates with the lake formation API and gets short-term credentials. And the second one is something called as a record service. So when you are reading data back, something needs to filter the data out for those columns which you don't have access to. So we built a new agent that sits on an EMR cluster as a privileged process called the record service that is filtering out this data from S3 that the user does not have access to. And no user gets access to these privileged processes. So today, it works with the Glue data catalog. It also works with Spark SQL, and it also works with EMR notebooks and Zeppelin with Livy. So it works in reality, doesn't work in my demo, though. All right. The next thing we did was on the security side, we added a configuration that allows you to block public access. what we noticed a lot of customers doing, probably not intentionally, is EMR comes with the firewall. The firewall is closed by default. You don't have any access to the firewall. But to reach native web UIs that are on the master node, customers sometimes open firewalls to quad 0 ports. That means they're open to the entire world. And that becomes an easy target for any kind of compromise. So we created kind of an account-wide switch. If you flip that switch, your customers will not be able to switch on clusters with a really open firewall port. The way it works is it allows you an exclusion list. That means only firewalls to this particular ports are allowed to be open. We also added native EBS encryption. So for those of you who have been using LUKS encryption to encrypt data that is sitting on local disks, now you don't need to do that. It's a pretty simple way to enable EBS encryption, and that also saves a little bit of compute. So if you look at what we have done consolidatedly on the security and the cost side, so we have done Spot, we have done managed resize, we have added fine-grained access control with lake formation, we have done block public access for unintentional network access, we have added EBS encryption. So the security story on EMR is pretty tight at the moment. So let's look at the orchestration layer. So on the orchestration layer, the most common ones that we see are AWS Step Functions and Apache Airflow. Customers run self-hosted Apache Airflow, and Airflow has a connector for EMR that can allow you to submit jobs on the cluster. That connector or that API is called the Steps API. Steps API used to be linear. That means you can only step one job at a time. We have made that API parallel. So now you can step multiple jobs using an orchestrator into a cluster, thus utilizing the entire compute capacity of the cluster. Step functions also, if you have not used step functions for managing your orchestration, that might be something you want to take a look at. So earlier, you could only define step functions in JSON, but now we've also added a Python library that allows you to define workflows. So with step functions and EMR, now you can create complex orchestration workflows. You can create, scale, or modify clusters. You can submit jobs. You can have an asynchronous pipeline or a synchronous pipeline. You can scale up clusters. You can manage exceptions and retries, or you can reuse clusters as well. We have done some really good work on the notebook side as well, and Mert will show you a quick demo. So what we've done with the notebook, so we have a managed notebook product that allows you to run Jupyter or Jupyter Hub. In the managed notebook product, we have added an ability now to associate Git libraries and also add libraries or Python libraries directly from the notebook. So Mert, for you to show the demo. This time he'll do it while I'm tickling him.
Thank you, Abhishek. In this demo, I'm going to show 3 of the functionality that Abhishek just recently mentioned. We're going to show how to install notebook scope libraries using EMR managed notebooks. We're going to diagnose an issue without needing any direct connectivity with a cluster using the managed EMR Spark history UI. And then lastly, we're going to showcase some of the Git integration that we put into the EMR notebook service. So from the EMR console, to get to a notebook, you just there's a link here. Click on it. You can create a notebook. You can create one for multiple people, or you can create one for each. And this is the managed notebook here. So one of the things, EMR comes with a predetermined set of libraries that your users can use. Uh-oh. I'm going to have to restart the kernel. All right, we'll just skip through that. So this function, if it was to run, would show you all the different packages that you have available on your EMR cluster. And what you could do is if one of your users need access to a library to be able to do some plotting or to use pandas or some other library to help them get their work done, they can install the Python package directly into their notebook instance so that the libraries are available to that notebook instance. I'm guessing that's not going to work either.
Well, I jinxed it by saying the demo gods have been good to us.
And then they can go ahead and use those libraries within this notebook. And it's scoped just to this. If this demo was going to work, we would have installed pandas and matplotlib, and then query some data and plot that graph. Oops. Now let's hope this works too. So the next thing I'm going to show is, no, I don't want to terminate. The next thing I'm going to show is the Spark History UI. You can get access to the Spark History UI from the EMR console. Again, you don't need to do any SSH tunneling or fiddle around with Foxy Proxy or anything like that. It's going to be available to your users without any of that direct connectivity. So to get to it, you just click on this link, and it will open it up. The great thing about this functionality is that it will be available even if the EMR cluster has been terminated. So if you have a transient cluster, it runs, it closes down, there's some issue with that cluster, getting access to those logs could be a little bit painful. But now we store the information about your jobs, and then you can get access to it through this UI, and your users will have the experience that they would expect if they had direct connectivity to the Spark History UI. So in this case, I'm going into this one job. This was the job that we were supposed to run. And then you can go and kind of diagnose and deep dive. In this case, we see some abnormal GC time for this job. You can get access to all of the logs for the executors, so your users can now kind of dive into it without possibly reaching out to someone else for this information. All right. The last feature I want to demonstrate is the Git repo integration with EMR notebooks. So if your users are sharing data or they want a repo to get version control for all of the data and the notebooks that they're creating, we've provided that functionality straight in the notebooks. So what I'm going to do is, there's a link on the left-hand side for Git repositories. We're going to add a repository. I've already pre-populated it. Give it a repository name, your Git repository URL, the branch that you want to check out into your notebook. If it's a private repo, you'll need to provide credentials. We use Secrets Manager in order to store your secrets, and then use that to connect to the Git repo and clone that. So in this case, I'm using a personal access token. Let's go ahead and add that repository. The next thing we want to do is link the notebook. And if you scroll down, you'll see that it's now linking to my notebook instance. And then this should only take a few minutes or a few seconds. What this will do is go clone the repo and make it available in your notebook instance. And now it's linked. Now if I go to my notebook instance, do a quick refresh, you'll see that a new folder has been created, which is the code within my repo. So you can do some pretty interesting things with Git other than check out and commit code. So suppose I have a piece of code here, a very simple ETL job. It's going to read some data, read that data in CSV, and then write that data out to Parquet. But suppose I want to make a change to this code. So instead of furniture, let's do home. We'll save this. And then on the left-hand side, we have a Git tab. We can go look at it. This is the file that I've changed. See the diff before committing it. So let's go ahead and commit that. I'll stage it. Commit the code. And then now I'm going to push it to my Git repo. Done. So what I've done here is just created a very simple example of how you can kind of integrate that with code pipelines, but you could use any other build system. So this code pipeline, what it will do is it will pick up any commits that have been done to your Git repo, It will go ahead and convert the notebooks, because when you're saving the notebooks, there's a lot of metadata within that notebook. So this will just strip away a lot of that metadata and add any code that may be needed to run. This build step will start up an EMR cluster, submit that code to the EMR cluster, run it to make sure everything is good. Next step would be an approval stage, so it's a manual approval. So if you need CR done or anything like that, that could be done here so that someone can go and approve this change. And then lastly, you can have that change deployed either to a location in S3 or to another Git repo if you want that code to be available, let's say, to a wider audience publicly or within your organization. So some pretty interesting use cases here. Abhishek?
All right, so in summary, we showed you all the optimizations, or some of the top 10 optimizations that we feel we have done in the last year. So we showed you things around improving Spark performance, adding transactional semantics to data in S3. We showed you better spot integration. We also showed you fine-grained access control with, on multi-tenanted clusters with lake formation. We also showed you native EBS encryption and an ability to block unintended network access. We also added step function integration and integration with parallel steps. That means you can run steps in parallel. And on the notebook side, we showed you Git integration and ability to run notebook scope libraries. And last but not the least, we added that off-cluster persistent Spark history service, which Mert showed you. So remember that Spark history service is a native component of Spark that runs on the master node. But for a lot of our customers that run transient pipelines, or when the cluster fails, what do you do with logs? So the Spark history server, we actually took the Spark history server outside the cluster, put it on the console, so even if your cluster has died, you can go back to the cluster, or if your cluster ran 2 days ago, you can go back to the cluster and you could look at all the logs and all the DAGs from the Spark history service. Well, that's our presentation. We are happy to take any questions. Thank you very much.